A smooth, uniform vertical hoop of radius little r and mass big M kilograms stands in a vertical plane on a horizontal surface. The hoop treads two small rings, each of mass little m kilograms. The rings are released from rest at the top of the hoop. When the two rings have each fallen through an angle of theta degrees on opposite sides of the hoop, show that the normal force of reaction exerted by the hoop on each ring is mg into 3 cos theta minus 2 newtons, where this force is taken to act in the outward direction from the center of the hoop. Okay, let's look at the forces acting on this ring. Well, we obviously have its weight, which is vertically down. It's its mass little m times g. Now notice that the outer part of this ring is in contact with the hoop. So that means that the hoop exerts a force on the outer part of the ring in a direction that's perpendicular to the surfaces of contact. So we have a contact force here on the ring. It's perpendicular to the surface of contact. So at this instant the ring has a velocity vector which is tangential to the circle. So this force, which I'll call r, is perpendicular to the velocity vector at this instant. Now it's a fact that the line joining the center of a circle to the point of contact of a tangent to the circle is perpendicular to that tangent. So that means that this vector r lies on the line joining the ring to the center of the circle. Now these forces are in the wrong proportion actually, and I'll explain a bit more about that later. The reaction force should be smaller in magnitude than the weight. We'll see more on why that is so later. Of course, it doesn't matter if you draw them incorrectly, but you get a better idea of what's going on, of course, if they are drawn in proportion. Anyway, let's suppose that at this instant, when this ring makes an angle theta with the vertical, its speed is v. So it's sliding down the circle. Its velocity vector is of course tangential to the circle. The magnitude of it is little v. Now I will remove this to make it easier to read the diagram. Of course the speed of the other ring is also v by symmetry. Let's look at the resultant force vector on the ring at this instant. Its magnitude is f. Now we explained in previous videos that for an object undergoing non-uniform circular motion, as this one is, the ring starts at rest, so speed is 0 and it speeds up. Anyway, the component, this force has a component that's pointing towards the center of the circle. So if we project the tip of this vector onto this radius line, we'll see that f does have a component that's pointing towards the center. So that's why vector r and vector mg must look something like what I have in this picture. So, so that when we add these two vectors, we get a vector which does have a component pointing towards the center. We saw in previous videos that this component has magnitude mv squared over r, where r is the radius of the hoop. Okay, it's got the same magnitude as the resultant force vector if the ring was moving with a uniform speed, if its speed was a constant v. So this is the component of the resultant force that we are interested in. We won't be interested in the other component. We are going to resolve the forces along this line. Okay, we saw in the previous video that the magnitude of the component of the resultant force along a particular line can be found by getting the magnitudes of the constituent components or force components along this line. So there are two forces acting on the ring. Let's get their components along this line. Well, we project the tip of mg onto the line. See, this angle is theta, same as this. We have a pair of z angles. We multiply the magnitude of this vector mg by the cos of theta to get the magnitude of the component of mg along this line. So we'll make this positive. We'll assume that if a component points towards the center, it's given a plus sign. You can put that in if you want. Now let's look at the component of vector r along this line. Well, vector r lies along this line. So the component of r along this line is r itself, but it's pointing in the opposite direction, away from the center. So we can say it's vector minus r. Okay, and if we put these together, we get the component of the resultant force along this line, which is pointing towards the center. It's positive, so it's plus mv squared over r. So in other words, if we take the component of mg along the line, this here, and subtract the magnitude of this vector, we will get the black vector there, which is mv squared over r. It's fairly clear what's going on. So you see, we don't have to worry about the other component of vector f, the component that's perpendicular to the vector line. We don't know how to get that anyway, so, and we don't need it. Now you see that we want r in terms of theta, not in terms of theta and v, the speed of the particle. So we need some more information here to eliminate v. So we just have r in terms of theta only. Well, that's where energy conservation comes in. Now in the previous video I explained in detail why we can use energy conservation. I said that in that example, gravity was the only force that did work. Gravity was the only force that had a component in the direction of motion of the particle. As you can see here, when the particle, or well, ring here, is in this position, its direction of motion is tangential to the circle. You can see that the weight vector does have a component in that direction. And it's the only force that has a component in that direction. The other force acting on the ring is this contact force R, that's perpendicular to the direction of motion. So there's no component in that direction. So gravity is the only force that has a component in the direction of motion of the ring for each instant of the ring's motion. And therefore we can use conservation of energy. So, okay, let's look at the initial position of the ring. Well, it started out up here at rest. Its initial speed was 0. Let's consider the total energy of the ring in this position. Let's call the initial position position 1. So the kinetic energy at 1 plus the potential energy at 1 is equal to the total energy at position 2 when it makes angle theta with the vertical. That's kinetic energy at 2 plus potential energy at 2. Okay, the kinetic energy at 1 is a half the mass of the ring times 0 squared. What's the potential energy at 1? Well, we need to refer the ring to some reference level. Now you might think that a good reference level is this line here, but you see, we don't want to rule out the possibility of the ring going down below this reference line. So it might be a good idea to take the reference line as the ground here. So that will include all the situations where the ring is, below the center of the circle. Now, as a reminder, the radius of the hoop is r. So to get the potential energy at position 1, we multiply mg by the height, which will be the sum of the two radii, the diameter, which is 2r. And that equals the kinetic energy at position 2, which is a half m times v squared. We're saying that at this position the speed is v. That's the v up here, of course, plus the potential energy at position 2. So what's the height of the ring above the reference level at position 2? Okay, well, this distance is r, and we have to add on this distance here, which I've shown in brown. How do we get this distance? Well, the radius is r. If we multiply r by cos theta, we'll have that distance. Theta is some acute angle here, so we don't have to worry about the cos of theta being negative or anything like that. Cos of theta will be positive. So we multiply this the hypotenuse of this right angle triangle, r, by the cos of theta. This is 0, obviously. Notice that our problem is independent of the mass of the ring. Doesn't matter what m is, it cancels out. Now we can subtract gr from both sides. So we get a 1 gr on the left hand side. Now we want to get v squared in terms of theta. By the way, okay, we have v squared over r here. So the quickest thing to do would be to sub in for v squared over r. So let's fix this up so we have v squared over r here. That means we have to divide everything by r and multiply everything by 2 to get rid of that half. So there's the division by r. Now multiply by 2. So I'll bring over this term here. This is 2g cos theta. And on the right hand side we have v squared over r. Okay, I'll copy this thing down. So we get rid of v squared over r here, and we replace it with what we just got. So now we will just have an equation involving r and theta, so we can get r in terms of theta. So we replace v squared over r with 2g minus 2g cos theta. Okay, we shift over this mg cos theta, and we can gather up and change signs. So the magnitude of the reaction force is 2mg minus 3mg cos theta. Now obviously we can factorize mg out of this equation. And don't forget to change the sign, so this is the desired result. So this is the magnitude of the reaction force as a function of theta only. Before we carry on, let's look at this more carefully. Now, the magnitude of r will actually drop to 0 when the thing inside the brackets is 0. So let's see when that happens. Let's see what value of theta makes this thing 0. So this is more of an aside, but it gives some insight into this problem that's useful. Okay, so we set what's inside the brackets equal to 0, and you can see from that that cos of theta will equal 2/3. And let's get an estimate for the value of theta that makes r 0. To one decimal place we get 48.2 degrees. Now I've just cleared the picture so we can see what's going on when theta is 48.2 degrees. So if r is 0, it means that this ring has lost contact with the hoop. So the hoop is no longer in contact, is no longer exerting a force on the ring. It's not in contact with it. Of course, the gravitational force is always acting. As a matter of fact, vector r was at its maximum when the ring was at the top. Can't show it here to scale, but vector r was actually equal to mg, the weight of the ring. See, the weight of the ring was vertically down. So for this ring to be in equilibrium at rest, these two vectors had to sum to 0. So r started out with its maximum value of mg. That value of r would decrease as the ring loses contact with the hoop. Okay, so we see that r can go to 0. Can r become negative? Well, it can if what's inside the bracket here becomes less than 0. So that will happen when theta is greater than 48.2 degrees. So this could become less than 0. So that means that r will become negative. Now, does that make sense? R, remember, is the magnitude of a vector. The magnitude of a vector is always a positive quantity. So how can the magnitude become negative? Well, in that case we'd say there are no solutions, but we can also interpret this quantity as a vector. Okay, so if it's a vector along a line, then it can have two directions, plus or minus. So if we think of it as a vector, r being less than 0 does make sense. So we'll have a vector pointing in the opposite direction to what it was when this quantity was greater than 0. So that could happen. So let's just see that situation on the picture. So 48.2 degrees is the threshold for this vector to go from pointing outwards to pointing inwards. So if we get a negative value of r, that's interpreted as a vector pointing in the opposite direction to r's original direction. So we no longer think of our equation as involving magnitudes, but now we can give meaning to a negative magnitude. Well, there's no such thing as a negative magnitude, but we interpret a negative value as a vector pointing in the opposite direction. And that makes sense for a ring, a small enough ring. If the object was just something rolling down a circle, like we saw in a previous example, then r becomes 0 and the object would leave the hoop and just fall to the ground. So the minimum value that r would have would be 0. But in this case we have a ring which is attached to the hoop, and if the ring's diameter is small enough, what can happen is that the hoop can press on this part of the ring. So the force on the ring due to the hoop is perpendicular to this part. It has to be inwards. The hoop is pressing, pulling on the ring, if you like. And indeed, by Newton's third law, the ring is pulling on the hoop. By the way, that doesn't have to happen when the ring is in this position. It could happen up here. So the hoop will pull on the ring, and by Newton's third law, the ring will pull on the hoop. Now in part 2, we want to show that the hoop will rise from the table if little m is greater than 3/2 big M. Okay, so now we need to look at the forces acting on the hoop. Okay, so this is the situation when theta is less than 48.2 degrees. Here I'm showing the forces on the rings actually. Okay, so the hoop presses on this part of the ring. It pushes on it, if you like. Similarly over here. Now we can apply Newton's third law to get the force on the hoop due to the rings. So if the hoop exerts a force on the ring, then the ring will exert an equal and opposite force on the hoop. So these two vectors have the same magnitude as this here, as r. So I'll write in that magnitude. Now, what other forces are acting on the hoop? Well, obviously we have its weight, which is big M times g. It's acting vertically downwards. Now, these are not the only forces acting on the hoop. The hoop is not moving. It's sitting here in equilibrium. So there must be a force counterbalancing these three forces. Well, obviously the hoop is in contact with the ground. So the ground exerts a force on the hoop that's in a direction equal, that's in a direction that's perpendicular to the surface of contact. That is vertically upwards. Now I can't show this vector here. It's getting a bit crowded, so I'll just show it over here. What is the magnitude of this vector? Well, it must equal the magnitude of the weight of the hoop, which is vertically down, plus the sum of the magnitudes of the two vertical components of these two forces. So if I add these three vectors together, I'll get a vector pointing downwards with a magnitude equal to this vector here. So I will call this vector n. Okay, what's the magnitude of the vertical component of this force? Well, we have a pair of z angles here, so this angle is theta. So we have a right angle triangle. We multiply the magnitude of r, which is, I'm just calling r, times the cos of theta. And it's the same story over here by symmetry. So we have r cos theta plus r cos theta plus mg. So that's 2r cos theta plus big M times g. Now we don't have to worry about the horizontal components, of course, because they'll just cancel out, because there is no motion of the hoop in the horizontal direction, no acceleration in the horizontal direction. So now notice here that this is an equation involving magnitudes. So, you know, it's assumed that n is some positive number, r is some positive number. And that's certainly the case for this picture. But, as I mentioned earlier, things could change if the rings move far enough down the ring, down the hoop. At one point, r drops to 0, and after that, r reverses direction. So the rings are pulling on the hoop. That's provided, of course, that the diameter of the ring is small enough, and it's assumed to be quite small. If the diameter is very large, if we've a big ring like this, obviously when r drops to 0, the ring may not make contact with the hoop again. So anyway, that's why the ring has to be small. Okay, so in this situation, the ring could pull on the hoop, and by symmetry the same happens on the other side. So that could happen. And it could happen that the pull on the hoop could be so big that this force drops to 0. In other words, the ground no longer exerts a force on the hoop, because the hoop loses contact with the ground. But you see, vector r has now reversed direction. R was pointing towards the center, and now it's pointing outwards. So that means that this quantity r could become negative. So it's no longer meaningful to refer to this quantity as a magnitude. A magnitude is always positive. And that's exactly what's going to happen when the hoop loses contact with the ground. In other words, when n goes to 0. So what we do is we set n equal to 0. And you will see that r will have to be negative. Actually, it's clear from this equation that r will have to be negative. Well, assuming cos of theta is not negative, because we get 2r cos theta equals minus big M times g. Well, this is a negative quantity. Big M is positive, g is positive. This is negative. Okay, and if cos theta is positive, which it will be if theta is an acute angle, less than 90 degrees, then r will come out to be negative. So we have to reinterpret r not as a magnitude, but as a vector. It's a vector pointing in a direction opposite to what r was originally. Okay, so we want the contact force of the ground on the hoop to be 0. So let's see what the consequences of that are. So we can plug this expression here in for r. Okay, remember what we're trying to do. We want to show that the hoop will rise from the table. In other words, the force N, the contact force of the ground on the hoop, will drop to 0 when little m is bigger than 3 times big M over 2. So how do we proceed? Okay, we've set n equal to 0. So how do we show that when n is 0, little m has to be 3 times big M over 2? Well, we could imagine that we want to find the angle theta that gives n equal to 0. So we could solve this equation for cos of theta. So this would be a natural step in solving this problem, even if we don't know exactly what it will lead to. To find the angle theta for which this vector reverses direction and the rings are pulling on the hoop in such a way, well, to such an extent that this force N drops to 0. In other words, the vertical components of these two forces will be upward and big enough to overcome not just the weight of the, well basically the sum of these two components has to be big enough, bigger, at least as big as the weight of the hoop. So what angle causes that to happen? So we could try to solve this for cos theta. So it's not 100% clear why we would do that, but this will actually answer the question for us. Now, to find theta, we first of all have to get cos of theta. We see that this is a quadratic equation in cos of theta. We have a cos squared theta term, we have a cos theta term, and we have a constant. So it's got the form of a quadratic equation, and cos theta, the coefficient of cos squared theta is a, the coefficient of cos theta is b, and the constant term that doesn't involve cos theta is c. So here's our formula for the solutions of a quadratic equation. So we're solving for cos of theta. So it's minus b, that's minus 4m or plus 4m, plus or minus is the square root of minus 4m squared, which is 16m squared, minus 4 times a times c. That's going to give us minus 24 little m times big M, and the whole lot is divided by 2 times a. That's 2 times 12m. Of course, the g's have been cancelled out all the way across here. Now here's what's interesting. We are solving this equation for cos of theta to find the angle at which for which the hoop loses contact with the ground. And now we can actually answer the question, because to find that angle theta we have to get the square root of this quantity here, and we will only have a solution, we will only have an angle, a real angle, when this quantity in here is positive, well, greater than or equal to 0 actually. So if that's the case, then we can find angle theta when vector n becomes 0. So all we have to do is solve this inequality, 16m squared minus 24 little m big M greater than or equal to 0. See, if this thing is negative, we have the square root of a negative quantity. That's going to be a complex number. So we'll have complex number value for cos of theta. which won't solve our problem. So we can rearrange this inequality to prove the result. So we see that the mass of each ring must be at least 1.5 times the mass of the hoop if the hoop is to lose contact with the ground when the rings slide down the hoop.